In this video, we look at adding a test to the LiquidCrystal library. We'll start at Arduino CI LiquidCrystal and fork the project into my own personal repository. Then we will get the address for it and go open up Git and then clone. That will give me a local version of it. With that, I'll open the folder using VS Code. The first thing I need to do, open a terminal with Control-tilde, and then do a bundle install. I'd like to have it done in the local path rather than in the global directory. So I'm going to use the local so that the items get put into the vendor bundle area. Now that I have Arduino CI working, I can try running tests. /test.sh. This script runs a series of automated tests to verify that the library is behaving correctly. But there's not very many tests. There's a few here, but not as many as we would like. So I'm going to demonstrate adding additional tests. Which tests should we add? Well, the library is defined here, and I'm going to pick a couple of them, scroll display left and scroll display right. Tests get added in the test directory. For our purposes, as described earlier, we have a test for the base class that simply includes common. Then we have a test for the test class that includes common and perhaps some more things. In this case, we expect the behavior to be the same for both the base class and the test class, so we'll put it in common. The common has a series of includes, then a series of constants to specify which pins or mock pins we're using. The God mode is a characteristic of Arduino CI that allows us to monitor the pins. I'm going to create a pin log that captures ints, an integer that it represents the data that I'm interested in. With the LiquidCrystal, the values are available to the device when a particular pin, the enable pin, is pulsed. So we're going to say each time that that pin is set, we will capture the various other pins in an integer. So we'll start out with a value of 0. We'll take the RS pin, add it in, then we'll shift it 1 bit to the left, add the RW pin, and then shift and continue adding and shifting until we get the 8 data pins and the RS pin, which signals whether we're in a data or command, and then the RW, which signals whether we're doing a read or a write. In our cases, we'll always be doing a write. Commented out is a couple lines that says, let's give ourselves a 16-bit array of the values, a bit set, and then output the bits in such a way that we can actually see the binary values. We already have a few tests that we can look at, possibly to use for examples. I'm going to use the begin function. If we go look at the various functions available in the API for the LiquidCrystal library, there is a begin function that takes 2 arguments, the number of columns and the number of rows. So here I have a unit test that tests begin passing it 16 and 2. How do we go about doing that? Well, state, we will reset. Well, what is state? State is the God mode. This is the mock Arduino board that is represented in software. From there, after resetting the state, we will create an object that is a bit collector. And the bit collector is the subclass that we created earlier, a subclass of DataStream Observer that will capture various values to a log. Now, the log is a global log, which will be available for use outside this class. Then we will reset the log index to 0 so that if the log had been used at all in the past, we could reset it and start over again. Next, we create an instance of LiquidCrystal test. This is the name of the class that will get replaced during the tests with either the base class or the test class, the production, the test, or the CI, or the base. And the name of this object will be LCD, and we are going to instantiate it, call the constructor with 6 arguments, rs, enable, and d4, 5, and 6, and 7. Then we will add an observer to this. So the state will observe, and whenever this bit changes values, it will call our function. It will send a message to our subclass. Then we'll execute the code we want to test, and then we'll remove the observer. So we will be collecting data that is sent to the pins during this single command. The data will look like this, and we can observe that by uncommenting out this logging lines. At this point, we'll run the test. So we have 0 failures, as before, but the interesting thing is the data that's coming out. So during the begin test, we're getting a series of numbers, 48, 48, 48, 32, 32, and so on. Those numbers are repeated here in the comments. We'll look in a little bit more detail as to how that's used. But then we have an expected, an assert, and then we increment over them to see if we got them. So let's take and make a copy of this function. We'll name our test scroll display left, since that's the function that we're testing. And let's go look a little bit at that. So this scroll display left does not take any arguments. So we can take that. We'll go ahead and do a reset, create our bit collector, reset the log, instantiate the object. But what we're going to do is we're going to take the begin and put it outside the observations. We don't need to observe the begin because that's already been done. Instead, what we want to do is observe the scroll display left. And then we can turn the observer off. And then rather than hard coding 12 in several places, I'm going to say const int expected size, and I don't know what the size is going to be. So I'm going to delete these and then make the array here, assert that the index is that, and assert that. So let's go ahead and save and run this. Then when we run it, we'll look for the output that happens during the scroll display left. So here, scroll display left had a 16 and a 128. So let's capture those two lines and then take them And in our scroll display left test, we will add these lines, line them up to be a little consistent with this. Then the number of bits that we're actually collecting in the bit collector is 10 bits. We're getting the 8 bits of data plus RS and RW. So we don't need all of the bits. We only need 10 of them. So here we're going to delete 6 bits from the front, and so that leaves us with our 10 bits. Another thing is, even though we're collecting 8 bits of data, we're actually only using 4 bits. The LCD library allows us to connect to the device either in 4-bit mode or 8-bit mode. We're using 4-bit mode. So we're going to delete the 4 bits from the right, since they are being ignored, and let's space out our bits a little bit so that we have our R, our RW, and then our data. Now the data, since we're actually doing 4-bit mode, we get the high order 4 bits, and then in the second command we get the low order 4 bits. So here is a nice way of saying these are the 8 bits. They're coming here, 0001100 means something. Okay, so now I'm going to delete the rest of the comments and go see if I can figure out what these bits mean. So I'm going to go to Wikipedia and do Hitachi 1602 LCD Wikipedia. Okay, and the 44780 LCD controller has a nice summary of the instruction set, where we can see RSRW 000, and then if we have 3 0 bits followed by a 1, then we're in the cursor display shift instruction. And in that case, the remaining 4 bits represent the SC, or display shift, and shift direction, where the last 2 bits are ignored. And we can see SC. What are the meanings of these? SC being 0 means move cursor, being 1 means shift display. RL, if it's 0, it means shift left. If it 1, means shift right. So going back to look at this, we have 3 zeros and a 1, followed by a 1 and the zeros. So this means 1, SC being 1, means shift the display, and RL being 0 means shift the display left. So we can say shift display left. So our expected size is now 2, and the expected values are 16 and 128. And then we'll assert that we actually got what we were expecting. So we'll come down, try running this test again. So for the scroll display left, we have 16, 128, the size was expected, and the 2 pin logs had the expected values. So the scroll display left function worked properly. Now, let's see if we can create a test for scroll display right. Scroll display right, and in this case, we'll say scroll display right. And now I'm going to anticipate what I think the values will be. Recall that we're sending 2 lines, 2 commands, and I expect this to be having the upper 4 bits, 4, 5, 6, 7, represent the lower 4 bits of the actual command. So to 128, we'll add 1 more bit, which will be 192, and I expect when we take off these 4 bits, move this over, then we will have these bits set, and that will be interpreted as shift display right. Now, let's go back and comment out the logging information. After commenting out the logging, we're about ready to make this our final. let's do a format just to make sure that it's properly formatted, since we have a GitHub action that will test that. Then we can run our tests one more time. Okay. As we look at this, we see that the scroll display left was okay. The scroll display right says not okay. We expected 128 but got 192. So that tells us that we changed the comment but not the actual expected value. So let's change the actual expected value and try running the test again. Now, at this point we have 0 failures and a clean set of tests. Now, let's think about how we're going to handle this in Git. We have one file that's changed. We've added 2 functions to the common tests. Right now, we have uncommitted changes on master. As a general practice, it's best to submit changes on a branch, so that if there's further changes to master, you can keep your master consistent with the upstream master. So we will branch and create something for scroll display tests. So we'll have a branch named scroll display tests and say add tests for scroll display left and scroll display right. Going to go ahead and push those changes up to my GitHub repository. When I go then look, there's something that has been pushed less than a minute ago. I'm going to go to the GitHub actions. I'm going to go ahead and enable them so that I can see that my tests are working. After enabling the GitHub actions, let's try going in and editing things slightly to see if we can push again and have the actions actually run. And then I'm going to save. I'm going to come here, add, push again to try GitHub actions. We've pushed again. Now let's take a look at LiquidCrystal, and we can now see that there's 2 actions. So we need to push twice to enable the actions on our fork of the repository. It may be that there's some actions that should only be taken on the primary repository from which we fork things, and we wouldn't want some actions to take place, but here we do want our tests to run so that we can have some confidence that when we put in a pull request, it will be available. So here I have a Clang format that verifies that we've actually formatted the code properly. That took 27 seconds to run. Now we're running the Arduino CI tests, and that took 26 seconds to do the tests, and now it's doing the compile to see if the code we wrote will compile on the Arduino. We know that it compiled in order for the tests to run, but that was on an x86 Ubuntu environment as part of GitHub. Here we're actually compiling the tests as if they were going to be pushed to the Arduino board. That appears to have run cleanly, so now we can say that both of our actions, both of our tests completed. So let's go look at the pull requests, and we have compare and pull. We'll put in our scroll display tests, and we're going to be requesting a pull from the scroll display tests branch of my personal repository into the Arduino CI LiquidCrystal master. So I'll create the pull request, and here we have our 2 commits, and now we can see that it's going to run the tests again in the Arduino CI repository, and that will give the maintainers of the Arduino CI repository confidence that they can merge things. So those are the steps that you would go through to add a low-level test. Again, what we've done is we've just captured the actual bits that get sent, the pins that get set. This is not writing the test before we implement the code. And in fact, our only real verification is when we go look up in Wikipedia to see if we think this is the right thing. For our purposes, this is sufficient. I'm comfortable that this library works properly and that it's doing the right thing. At this point, we're not so much adding tests as if we're developing the library, but these are more regression tests so that in case we break something, we'll find out. So we're verifying that the library works the way it did originally. And for these low-level tests, that's satisfactory.